I'm Hongrui Zhao, a PhD student from UIUC. I'm presenting our work RAMEN, Real-Time Asynchronous Multi-Agent Neural Implicit Mapping. The motivation for multi-agent mapping is autonomous robotic exploration, which is relevant to both search and rescue mission, as well as planetary exploration. So, how does multi-agent neural implicit mapping works? Let's say we have two robots, each robot using its camera to capture a local dataset and use that data to train a neural implicit map. For multi-agent mapping, they also share their neural network parameter with their neighbors and try to achieve a consensus with their neighbor in the sense that both neural implicit map will eventually converge to the same map that represents the entire scenes. For this distributed neural network optimization, existing work commonly use CADMM algorithm, which have a pair of agent I and j, agree with a consensus target Zij, and this Zij is just a simple average of the two neural network. And then it performs primal and do update to minimize the map reconstruction loss while reaching the consensus target. It works well in simulation, but does this method actually work in real world? So to investigate that, we perform hard experiments. We first have one robot exploring the seams, and this is the reconstructing map. We use this as our ground truth. And then we have two robots, each explores half of the seams. And because of the communication constraint, each robot only gets one communication every 30 seconds. And this is the reconstructing map, which completely diverge. So the question is, how do we deal with this real-world communication constraint? For our method, we first provide some intuitions on the consensus. Let's say we have agent I and its neural network. We render a map out of the neural network. It looks like this, where most of the neural network parameter correspond to a region well reconstructing, but some of the neural network parameters correspond to the region that hasn't been explored yet. And then we have our neighboring agent J, and because of the communication disruption, we haven't heard from it for a while, so we only have a really outdated copy of its neural network. And its map looks like this, where most of the neural network parameters correspond to a region poorly reconstructed, but maybe some of them still have valuable information. So if we simply use CADMM, then our consensus target Zij is a simple average between these two neural networks, which degrade the good information containing both of them. So the question is, can we do some kind of weighted consensus that favor the parameters with higher quality information? To do that, we represent our scene with a feature grid. To query a point in the scenes, we find the neighboring vertices. We interpolate their values and pass them to MLP decoder to get color, volume density. Our first intuition is that the uncertainty of an area decreases with the frequency of observations. Our second intuition is that the update to a vertex happens when robot visit its corresponding locations. So more often the vertex gets updated, the more often the robot visits locations, the more certain we should be about that vertex. So we use this frequency-based uncertainty that simply use the number of gradient updates a parameter gets as its uncertainty, and we normalize it to get our weight. Here's a visualization of our uncertainty. Purple means certain and blue means uncertain. It divides the seams into a low uncertainty part and a high uncertainty part, and this corresponds well to the actual reconstructed map. With this weight, we can perform weighted CADMM. So instead of the simple average as our consensus target, now our consensus target becomes a weighted consensus. And then we can perform weighted prime and do update, so we favor the neural network parameters with more certain information, and we mitigate the bad influence from outdated neural network due to the communication disruption. Here's our hardware experiment results. Each robot managed to map the entire scenes using its own observation and the information shared from its neighbor. And this is our final map, which achieved comparable performance to the ground truth. Our method is also quantitatively much better than the baseline. Some takeaway for RAMEN. First, communication disruption are challenging. Second, the weighted CADMM can help with the challenge. And finally, the simple frequency-based uncertainty is good enough to improve the performance. Thank you very much.